Multivariable calculus, we're looking at section 15.4. We're really going to deal with working with polar coordinates. Sometimes it's much easier to approach an integral using polar coordinates as opposed to Cartesian rectangular. There are several helpful formulas linking the rectangular and the polar coordinates. We're so used to saying move x steps to the right, moving y steps up. But of course, we saw this in BC calculus as well. Here's r, and here's x, and here's y. We know from the Pythagorean theorem that x squared plus y squared would always equal r squared. But because we dealt with this so much last year too, you might remember x was always equal to r cosine theta, y was equal to r sine of theta. Also from trig, we could say that the tangent of the angle, should we ever need an angle, plain and simply could be y all over x. So just a little bit of review dealing with what's happening with polar coordinates. And polar coordinates, of course, rather than having a x comma y, we could have an r comma theta, a radius and an angle. So, what we've been dealing with so far in regard to, working out our integrals is, of course, we've been dealing with very familiar curves that really didn't deal with circles so much. I guess what I want to begin to get into right now is we can have a polar rectangle. When you have a polar rectangle, it can look way different than the rectangles that we're used to seeing. A rectangle that we could form, even if it was the base of a rectangular prism, was always x by y. And, what we'd see most of the time was that x was between two numbers a and b, and y was between two numbers c and d. And then we could have a rectangular subregion and so forth. You see the following, consider the following polar rectangles. We look at this circle, and the very first thing we think, of course, is, my word, why in the world are we even calling this a polar rectangle? Well, again, trying to just give you that similarity that in Cartesian coordinates, our variables had some boundaries here. Now we're working in r and in theta. Taking a look here, we can say that if we've got this all darkened in, we could say r is strictly between 0 and 1. Here's a circle with a radius of 1 centered at the origin. How about theta? Theta would be guaranteed to be between 0 and 2 pi. So even though this is not looking anything like a traditional rectangle, we could call it a polar rectangle for much the same way that our two variables have boundaries, much the same way we had up here. Take a look at this next region. You can see that maybe we have a circle with a radius of 1, a circle with a radius of 2. I could say that the radii are bounded between 1 and 2. And theta, this time, you can see we're always above the x-axis. We'd be starting here at 0, going all the way out to pi. If we were to graph that out, we would get this polar rectangle. So that's just getting us started. So to integrate, we need to form a Riemann sum. And, we're going to ultimately investigate dA. dA, as we would look at that, if we were to look at this little rectangle in general, like a sub-rectangle, we're so used to seeing that as really delta x times delta y, or a dx times a dy, or vice versa. That's like a little dA. You can think, well, my word, can we come up with some way to look at this? Well, let's just say that your r is between two set given values. Here's a polar rectangle. R is between a and b, and theta is bound between alpha and beta. So we've got this little polar rectangle here. We could divide this polar rectangle into subrectangles, much the way we had done before in the start of chapter 15. And we could pick just a sample point to determine, a height, so to speak, to make a little rectangular prism. But if we went back to our trig days, you might know that the arc length of a circle was r times theta that we would be working with here. So we could have S is equal to r times theta. That's from geotrig, where theta is in radians. And what we're doing right here, let's just take a look at this particular little sub-rectangle. As we really begin to investigate that right there, this little arc length right here, that's your r times theta. Well, if this is d theta in there, that little d theta is, this tiny little way how theta has changed. So we could call that r d theta, and then coming this way, this is how our radius has changed. So we could say, wow, it sure kind of looks like we've got a rectangle, especially if we go small enough. Especially if we're going to go small enough. So you look right here, and that would be your little dA. And what are we seeing then? dA would be, as we multiply here, r dr d theta. And this right here is the critical link between integrating in rectangular form and integrating in polar form. What we're going to see right here is that when you have your dA, we're going to change that to r dr d theta. Everywhere where we have an x in the problem, we're going to change that to r cosine of theta. Everywhere where we see a y, we'll have r sine of theta. So you could see, this x up in here has become r cosine of theta. This y becomes r sine of theta. And our integral boundaries, well, we're integrating with r first. Our r's between a and b. Our theta would be between alpha and beta. Right now, this might even seem like we've made the problem considerably more difficult. In all truth, there are many problems where integrating in this form will make your problem way, way easier. So we're going to close right here. This was just the introduction, laying down the foundation as to how we're going to integrate in polar form.